let's circle back to these graphs of vapor pressure as a function of temperature. Talk about the equation that models these lines. It's known as the Clausius-Clapeyron Equation, and it relates vapor pressure, which we see on the left-hand side of the equation, to temperature, where the temperature is in Kelvin, as well as the heat of vaporization. The reason these curves have different slopes and accelerate upward at different rates is that the heats of vaporization of these liquids are different. And try to connect this with intermolecular forces. Ethyl ether has the lowest enthalpy of vaporization and increases in vapor pressure most rapidly, followed by ethyl alcohol, water, and ethylene glycol, which has the greatest enthalpy of vaporization and the slowest increase in vapor pressure with temperature. That's reflected in the mathematical forms of these equations, and I encourage you to think through this on your own, comparing to the graphs on the previous slide. And there are two forms of this equation that you'll commonly use, particularly chemical engineers will use this equation quite a bit. There's the single point version where you're looking for the vapor pressure at a particular temperature and you know the heat of vaporization. And then there's the multi-point version where we're given the vapor pressure at one temperature. Say we know the boiling point, right? This is an important conceptual point. If I know the boiling point, I know the vapor pressure at the boiling point. It's 1 atmosphere, the normal boiling point. You can find the vapor pressure at any other temperature, let's say T2, by applying this multi-point version of the equation where I've just taken the single point version and subtracted it from itself using 1 and 2 subscripts to throw in 2 vapor pressures and 2 temperatures. So you may apply this equation to find vapor pressures or find a temperature at which a liquid boils based on other data, things like this. It relates vapor pressure to temperature. We can also use the Clausius-Clapeyron equation with measurements of temperature and pressure to measure the enthalpy of vaporization, and this is very commonly done. In this problem, we're told that isooctane has a vapor pressure at 34 degrees C of 10 kilopascals and a vapor pressure of 100 kilopascals at 98.8 degrees C. And we're asked to use this data to estimate the enthalpy of vaporization for isooctane. So the important data is highlighted, the temperatures and the vapor pressures. And before we dive into the math, I want to draw a picture of the situation, as we often do. So here's a sample of isooctane in gray. Here's the liquid phase, and here are those molecules in the gas phase at 34 degrees C, which is 307.2 Kelvin. What happens at 98.8 degrees C? Well, before I reveal the picture, try to visualize it in your mind's eye. What's going to happen to this gas phase at the higher temperature? What's going to happen to the liquid phase? Well, molecules will leave the liquid phase to some extent and enter the gas phase. The vapor pressure increases because the temperature is higher. Think back to those graphs or our intuition on vapor pressure. So at 372 Kelvin, 98.8 degrees C, we have more molecules in the gas phase. And basically the difference between these two situations can be used to estimate the enthalpy of vaporization. So let's lay out what we know. We know the vapor pressure at T1, 307.2 Kelvin, is 10 kilopascals. The vapor pressure at 372.0 Kelvin, or T2, is 100 kilopascals. And I know the Clausius-Clapeyron equation. The natural log of the ratio of the vapor pressures is equal to negative delta H of vaporization divided by R, 1 over T2 minus 1 over T1, where I put T2, PVAP2 in the numerator here and PVAP1 in the denominator there. So essentially plugged in to the multi-point form of the Clausius-Clapeyron equation shown on the previous slide. To ensure that delta H of vaporization comes out in units of joules or kilojoules per mole, we're going to use 8.314 joules per mole per Kelvin for the value of the ideal gas constant, and when I plug and chug, I arrive at 33,800 joules per mole, or 33.8 kilojoules per mole for the enthalpy of vaporization for isooctane. And this is typical, pretty typical of a liquid, a normal liquid under typical conditions on planet Earth, something like tens of kilojoules per mole.